sort of go back to where we finished last time. And I just want to recall the algebraic part. And you can really define this for any set in Rn. It doesn't need to be definable. And we can take Z-alg to be the union of all A's, which are subsets of Z, which are connected, semi-algebraic, and positive dimensional. And the connected is kind of important because otherwise, technically, if you had something positive dimensional in there, then you could take it together with any point. And that would also be positive dimensional, and you'd sort of remove everything. So you only want to remove somehow the parts that really are positive dimensional. And I just want to remark that this set can be quite bad, at least in terms of thinking from an O-minimal point of view. And a nice example to think about is if you just take the curve, the surface z equals x to the y, and just not even to think about problems with logarithms and whatever, which are definable, and it's not really a problem. But let's take xy just in the interval from 2 to 3. So then this is just definable in Rn. And you can see that every rational y gives you a small piece of an algebraic curve, a rational curve. And so if I take z, big Z, to be that graph, then Z-alg, well, is not definable because it has infinitely many components and it has infinitely many pieces of increasing degree and so on. So this is, well, not a very, well, in general it can be not a very nice set. So now I want to again state the counting theorem. So this is a theorem proved with Alex Wilkie, and I want to state it in a number of forms. So we'll first take Z in Rn definable and epsilon positive. Then the conclusion is there exists a constant which depends on Z and epsilon, such that if you count the rational points on Z outside its algebraic part and up to height t, and the height t is just a very naive height of a rational point here. The height of a rational point is the maximum of its numerator and denominator written in lowest terms, and then on an n-tuple we just take the maximum of that. And it's bounded by this constant t to the epsilon. So it grows slower than any power of t.
Here it's just rational point, or you allow some points in some bounded degree?
I'm going to do that. Yeah, I'm going to do that. Yeah, so eventually there'll be a version of this. I've left room to write bounded degree. Here it's just rational. I wanted to do it that way first, but that will be crucial. Now I want to talk a little bit about how you prove this theorem. So first, this is, let's call this sketch. How do you go about proving this? Well, first, it suffices to consider your set Z to be in the open interval 0, 1 to the n. Now, why is that? Well, let me just draw the picture in 2 dimensions. Here's 1 and 1 and minus 1 and minus 1. And the idea is you can intersect Z with this grid. And so you'll have first the part inside this open 0, 1 to the squared. Now this part, you can consider, where the x's are too big, you can consider the set of 1 over x's and y. So you can reflect this into there and get another definable set. And this here too. And then the parts that are on the boundary, of course, you can go down lower dimension, and the height of 1 is just 1. So this is by reflection, plus or minus z, the coordinates, let's call the coordinates zi to the plus minus 1 will have the same height, and it's fully definable operation. So that's no problem. You can reflect yourself and have finitely many sets instead, all inside 0, 1 to the n, or possibly smaller n. Okay. So next, we're going to parameterize the set for some high value of r that's somehow best chosen after you finish the proof, because there'll be an iterative proof. So we're going to parameterize z for some large value, for some sufficient value of r. And just to mention that this step is really necessary, you can't hope to parameterize an unbounded set with bounded derivatives. I mean, all right. So now in the case of curves, so now we've got some 0, 1 to the k's. Now we can assume that z, if you like, we can divide it into its pieces of whatever dimension. Maybe we should have done that first. So we can assume that z has dimension k, and we've got some maps. We've got this parameterization, and it comes with some maps like this. And now we're going to want to do an argument like we did before, that if you take a smaller box, let's call it J is a small box in here, that the rational points up to height t and on this smallish interval all lie on one hypersurface. So in the 2-dimensional case, you could do this with the Vandermonde determinant and this mean value theorem of Schwarz. Here you can't do it, but what you can do, you're still going to have this, you're going to make the monomials on the phis and all the x's up to some height for some suitable degree of hypersurfaces. And so you get a large determinant, and you can simply expand it in Taylor series with remainder about some suitable point in here. So it'll have the Taylor coefficients will be some fixed numbers. And then you notice that in this determinant, there's an awful lot of cancellation. And so, for example, you can immediately see that the constant term cancels. And if you look at the linear terms, they'll all be a combination of a rather small number of linear forms. And so they'll be dependent on each other over the reals, and they go away in the determinant. And if you balance how this works out, and you take your Taylor series sort of far enough to see all the cancellation, and then you take a remainder term, you'll eventually see that everything in this determinant is rather small.
Is it the same argument as the Laurent interpolation determinant? It looks similar. The Laurent.
Yeah, I'm not sure. I thought that Laurent used complex variables.
Oh yes.
Because there's no maximum kind of principle here. It's a pure Taylor expansion. It's just real. So I think it's a bit different, but I think it probably leads to the same. If you do have access to complex variables.
Yes, we can do Laurent determinant just with the Taylor expansion at the origin.
Oh, you can?
Yes, so I think it's really very similar.
It's probably, yes. So all of this, again, shows you that if you take this to be small, but not so very small, everything has to lie on one hypersurface, and you conclude that Z, right. The rational points on Z up to height T lie on T to the epsilon algebraic hypersurfaces of some degree that you chose. Right, there's some, in a way you have to choose the degree first, and then you choose the R that's sufficient to R parameterize. I'm not going to, I'm not going to make those choices, but it's a finite process. And now what you want to do, of course, so on finitely lie on algebraic hypersurfaces of degree D. So these are some intersections of Z with some hypersurface W. And now what you want to do is repeat the argument with all of those. But of course here there's a whole family of sets that arise when you intersect Z with this varying family. And so you immediately find that you need sort of an improvement of this theorem. So now we're going to take Z to be a definable family. And the theorem will be that there's a constant that depends only on the family such that the same counting estimate holds on every fiber. So this is it's completely uniform in the family. Right. Now I want to say just a little bit more about this algebraic part. How does it sort of show itself? Well, the idea is that if you've got something algebraic in Z, algebraic part, then eventually when you intersect it with something that's algebraic of at least that degree, it won't go down in dimension. So you detect somehow this algebraic part when in this iterative process, at some point things stop going down in dimension. And to make that sort of clearer when that happens, you can instead intersect, instead of with hypersurfaces, you intersect with algebraic, hypersurfaces that aren't codimension 1. So maybe I should call them algebraic subvarieties of dimension equal to k, the dimension of Z. You intersect Z with things of that dimension. And the way you do that, you can be very crude about it, is simply take any k plus 1 of your coordinates and impose an algebraic relation there. So in fact, most of the things you get will be much smaller than the dimension k, but some of them will be dimension k. And then when you intersect an algebraic thing of dimension k with a definable set of dimension k, and if what you get doesn't decrease in dimension, then you must have found something semi-algebraic. And one way to see that very clearly is that you can cell decompose all of these families before you do any of these estimates. And so that you can actually find, when you intersect Z with something like this, that you will find cells of dimension k that are contained in some cell of dimension k of this. So that's what well, I used to call it a block, but this is a somewhat more refined notion. It means that you've got a cell which is contained in a semi-algebraic cell of the same dimension. And that means that any point, so this is the cell of Z intersect W, the bigger cell is actually semi-algebraic. So if you take some small disk about a point in the cell, then you're a fully semi-algebraic set, and you're inside Z intersect W, and you're dimension K, and you're in the algebraic part. So now we can do a little bit better again, because we can, instead of removing the entire algebraic part, all we need to remove are the algebraic things we found up to this degree that we needed. So instead of removing, so that there exists an epsilon and a definable family, W, which depends on Z and epsilon, with the property, there exists the constant and the definable family such that instead of W at a given fiber is always contained in the algebraic part of Z at that fiber, and all you need to remove is W. So even if your algebraic part isn't definable, somehow for each epsilon you only need to remove a definable part of it. And there's one further sort of refinement that I want to mention, and we will need it, which is that actually you don't need to remove all of that. So let's say that this W represents, up to a certain dimension, all the algebraic things that lie in Z, or up to a certain degree, I should say, up to a certain degree. But in fact, when you do this process, you generate t to the epsilon pieces at every stage. And those t to the epsilon pieces will be either smaller dimension, and then you continue, or they'll be in the algebraic part, and eventually you get down to points. So that in fact, Z Q up to height t is contained in, at most, this Z epsilon, t to the epsilon, of things that look like this. Cells of intersections that are contained in semi-algebraic cells of the same dimension, and which could be points. So let's call them blocks. So the positive dimensional blocks will be contained in these definable families. So they're definable families of these blocks, and some of them may be just points. All right. Right, and the final thing to say is that you can do it also with points of bounded degree. So here we're going to let, I'm sorry, I've used the same letter K. So K will be greater than or equal to 1. And instead of looking at Q points, I'm going to look at K points of Z, which is the set of x's in Z such that each coordinate is not necessarily rational, but generates a field of degree at most k, and the height of the xi's are at most h. And here this height is the so-called absolute multiplicative V height. It agrees with the height we had before, but just to say that there's also the logarithmic height, which will come up later as the absolute logarithmic V height. Right.
Capital H is T, in fact, or T is capital H. So.
Yes. And then we can take n, if you like, what's the good way to do it? N sub k of z and t to be the number of points on z of degree k and up to height t. And then we can state exactly the same theorem, but now with some k greater than or equal to 1 and epsilon positive. The family depends on k. The constant depends on k, and you count up to k. But it's fully uniform in the family. You can count the points, and also this, well, zkt is contained in that many blocks. So I just want to indicate sort of very briefly how you do that. Essentially, you count the points. Instead of counting points, if a point has degree less than or equal to k, then it's the zero of some polynomial of degree k. And you can instead form the definable set which controls the polynomials of degree k which vanish on the points here, real coefficients, and look for rational points on that set. So any point that arises here will come from a rational point on that other set, and then you just count them. And the map that sends a polynomial to its roots is semi-algebraic. Right. So, yeah, right. So just a couple of things before moving to the applications is to say that this theorem somehow looks quantitative, epsilons and constants, but it's sort of, it isn't really. If you like, this epsilon, the sort of the lower than any power of t growth, is something you get purely from the O minimality, just from the finiteness of all these, of the finiteness properties in O minimal structures. And in general, you sort of cannot make this effective, or there's no way to sort of improve it in general. And you can make examples where this z is analytic, and this t to the epsilon, so to speak, goes to zero. The epsilon goes to zero as slowly as you want. You can sort of just build very lacunary graphs that have lots and lots of rational points on some very lacunary series of heights. So there's somehow, in general, you can't really improve this statement, but it would be natural to ask whether you could improve it in particular O minimal structures that are more controlled. And so Wilkie conjectured, for example, that you can, it's natural when you see t to the epsilon to say, well, can I get a power of logs? That you can get a power of log for z definable in Rx. Because in Rx, you can't make arbitrary sort of lacunary constructions. In this sense, analytic things, one feels that analytic things are rigid, but they're really not that rigid. They're quite flexible in their own way. But here you really have only that one function and the things you can do with it. And in fact, this was proved more generally by Binyamini and Novikov and Zach. And they proved it more generally even for restricted sub-Pfaffian. So the Pfaffian systems are O-minimal structures where you can expect, where you say, well, I've got a system of differential equations, and they have these degrees. Every derivative is a polynomial of some degree in itself, and all the previous derivatives, and you've got, you've got something on which you can hope to hang these constants on, right, which is the degrees of all the things defining your differential equations. But just to say that in general, it appears that the sets you want to count on in the Diophantine applications are not definable in R-Pfaff. They're not Pfaffian. That's not a theorem. There are some positive results in that direction, but sometimes they are, for example, the parameterizing, uniformizing functions of abelian varieties are indeed Pfaffian, and you can get this sort of real control over this. I should say not only on improving, I've been talking about improving the quality of the bound, but even making this constant effective. And so just want to mention, maybe it'll come up again, but in relative Manin-Mumford, you can make some of these things very effective in recent results of Binyamini, Jones, Schmidt, and Thomas. So let's call that effective. And that's in certain Diophantine, I'll say a little bit about this relative Manin-Mumford, where the sets you need to count on are in an O-minimal structure where you can get really effective control of this process. All right. So I want to talk about Diophantine applications, and I guess I'm going to first talk a little bit about how this works in the Andre-Oort conjecture for counting special points. But then I want to get on to a truly unlikely problem. But I just want to say, so the strategy of doing this was proposed by Zanya in the context of Manin-Mumford. In Manin-Mumford, you're trying to understand torsion points of a lattice, and you can view those as rational points with respect to the coordinates given by the lattice. But I want to say that this counting theorem is, on the one hand, it's a Diophantine statement. It counts rational points on some sets. On the other hand, at least in that initial form, the first thing you do is throw away everything that looks remotely like a classical Diophantine problem. You throw them all away, and you just count on the rest. So I want to say that this strategy of using this for actual Diophantine problems looks, I think, is not very intuitive. Because you seem to be it's a Diophantine statement, but it only looks at strictly non-algebraic things. All right, so this strategy turns out to be good for some parts of Zilber-Pink, and for other parts, it's not so good, which I will explain at a certain point. So I want to consider the basic case of Andre-Oort and how this works out. So we're going to consider the uniformization of the nth modular curve to the power n by the upper half plane to the power n. And we're going to have a subvariety in y1 to the n. And we want to understand the special points that are on this variety v. The special points, right. And you may remember, so the goal is to understand the special points in V, and the special points for the J function are the sigmas, which are J of Z, for quadratic points in the upper half plane. And this will be the key, really. We're going to count quadratic points. We're going to change the problem from studying these singular moduli to counting quadratic points. Now, when you have such a quadratic point, then you'll have some minimal polynomial and I apologize for all the excessive z's. So this is the minimal polynomial of the quadratic, and it's over z, not over q. So these are integer coordinates, which are relatively prime. And when you have such a thing, it has a discriminant d of sigma. Okay, so the special point, the singular modulus, has a discriminant. Here we'll be looking at n tuples of singular moduli, and there'll be n tuple of discriminants, and so on. And this means that the corresponding elliptic curve, whose J invariant is sigma, has Cm by the unique quadratic order whose discriminant is that number, d, the discriminant. All right. So the general picture, maybe I should draw a picture here, which is down here you have y1 to the n, and you have a subvariety v. Up here you have products of the upper half plane. And this is the fundamental domain, the fundamental region of the J function. This is the Cartesian product. This is h to the n. And we're going to look at pre-images, and we know that the special points here, and there may be special subvarieties, the special points in any case will come from quadratic points. We know also that each point here, of course, will have infinitely many pre-images, right? Because this whole thing is acted on by SL2Z to the n, under which the J function is invariant. So every point down below corresponds to some SL2Z orbit in this space. But the point of the fundamental domain is that you can always find representatives in the fundamental domain. You can shift everybody in there. So now there are various ingredients you need to make this argument work. So let me state first the definability ingredient. Which says simply, so I'm going to take, I should have said this before, that Z, which is the inverse under this n-fold power of the J function of V, and intersect with the n-fold product of these fundamental domains, is definable. That's a definable set. And actually, it's definable, let's just say, in R and X. And just to mention that you can see that quite easily, it's very elementary in this case by the Q expansion of the J function. If you expand J in terms of e to the 2 pi I z, then it's a meromorphic function, but the e to the 2 pi I z is definable in a whole strip. And so then so that's definable, and then you're a convergent, well, meromorphic. But if you multiply through by Q, you're actually an analytic function that's over-convergent because this domain is far away from the axis. I've drawn it a bit further than it really is. I mean, it's not a very good circle. Okay, so it's definable. The next thing you need is a height ingredient. So the height, right. So our strategy is we've got a definable set, and the special points here are going to give us quadratic points on that set. Of course, the entire function cannot be definable because of this SL2Z. It's invariant under an infinite group. But everyone has a representative in the fundamental domain. After that, it just repeats. And so this is the set we're going to count quadratic points. Okay? Count quadratic points. All right, so what are the height of these points? So you need to control, if you have a singular modulus here, what kind of a point it gives you. Height of pre-image of a special point in the fundamental domain. So let me underline that and underline that. And it's very elementary in this case that you get something in the fundamental domain. I don't want to go through this too much. This is absolutely super classical. But you get a z in the fundamental domain exactly when this quadratic form is reduced. And reduced means, so z in f of n, in f. Okay, there's an n tuple, but we have to do this coordinate by coordinate. If a, b, c is reduced, and reduced in this case means that the absolute value of b is less than or equal to a, which is less than or equal to c. Anyhow, there are some very elementary conditions, and it's a completely elementary thing then. Of course, we know what the real and imaginary parts of the solution of that quadratic look like. They involve a, b, and c. And you eventually conclude that the height of the pre-image is at most 2d, absolute value of d. This discriminant, I should have said, is always negative because we're in the upper half plane. I mean, it's a quadratic order and so on. So a point here gives you a point here whose height is at most twice this discriminant. On the other hand, and this is the key point, one key point, that this point sigma has a rather large Galois orbit. And indeed, the degree of Q sigma over Q, and again this is super classical, is equal to the class number of the discriminant. So this order may not be the maximal order, so this is the Kronecker class number of the order, but it's essentially, so this is the class number of OD. And again, I apologize, this H is not the height, but this is the absolute classical symbol for the class number. So its size is, since famous result of Siegel, is bigger than or equal to a constant times d to the half minus epsilon for every positive epsilon. And this is famously ineffective. This is a famously ineffective argument because you have two proofs, or in the proof of this, you argue on whether there is or isn't a Siegel zero, a counterexample to the Riemann hypothesis. And if there isn't, you get one estimate, but if there is one, then it pushes all the others away and you get another argument. But this is sort of deeply ineffective without knowing that. And then this is basically the comparison. So what happens is if you get a special point, it has a positive power of this D conjugates, and each one of them has a pre-image in this fundamental domain, so you get, and they have height less than power of D. And that's too many, right? So maybe I should write it over here. Let's just say we can assume that V is defined over a number field, let's say of some degree D, because in any case, if V isn't defined over a number field, then all its algebraic points will lie on some subvariety, which may be reducible, but which is defined over a number field, which R. So you can immediately replace V by something defined over a number field. So if sigma now, which is a tuple, is in V, is a special point, and if I take my height h to be twice the maximal discriminant of all the sigma 1 up to sigma n, then I'll find that the number of points on Z of degree 2 and up to height h is at least, say, a constant of a quarter in Siegel's theorem over D, because only one of the conjugates over Q, 1 over D of them will land back on V, and I can take D to the quarter. So that's some constant D to the quarter. On the other hand, I can apply the counting theorem with epsilon, let's say, equal to a fifth, and that will give me a contradiction. So contradict the counting theorem with epsilon equal a fifth, say, and that's for D large, because you'll have D to the quarter things, but the counting theorem says you can only have D to the fifth things outside the algebraic part. So you get a contradiction unless there's something positive dimensional. Algebraic contains. Now the thing you get here of course in the counting theorem, I should have said you're identifying the complex numbers with R squared and real and complex parts and so on. So when you get something algebraic, it's only real semi-algebraic. But because V is a complex variety and J is a complex function, if you get something real semi-algebraic, you'll also get its Zariski closure. If you like, the complex function which vanishes on that semi-algebraic real thing will vanish identically by the identity principle of complex analysis. So it contains positive dimensional complex algebraic varieties. Again, in the sense that we've defined it in the upper half plane, they're not complex algebraic subvarieties of the upper half plane, but they're intersections with the upper half plane of truly complex algebraic things in P1 to the n. And so now we have to describe those things, and here we have a principle. So now this is if you like, it contains some positive dimensional algebraic variety W. So if you like, we have J of W. It's contained in V. And that's an exceptional situation because J is a highly transcendental function, and it's governed by this functional transcendence statement which goes by the name Ax-Lindemann, which says that the maximal algebraic W's contained in Jn inverse of V are weakly special. they're weakly special. And in particular, I mean, what it means is that if, let's say, if I call W angle weakly, the smallest weakly special thing containing, it's weak, so this is the weakly special closure. And I should have said I've defined weakly specials in y1 to the n involving definitions by modular polynomials, but up in the upper half plane world, it means they're defined by Möbius transformations with rational coefficients. So you're allowed to impose, well, in fact, I did sort of define them, right? You take a partition of the coordinates, some of which are constant, and the others, the other coordinates in their partitions are related by GL2Q plus, and then the images of those are the weakly specials, and so these are the weakly specials. Then the statement is that J to the n of W is Zariski dense in the image of that of the weakly special closure. And so if J of W is contained in there, then this has to be contained in there. And it means that in V now, all the algebraic exceptional things are on weakly special things. And so the exceptional case in the counting is lining up exactly with the exceptional case, the Andre-Oort, because the weakly specials that contain special points are special. So you have to complete this. So to complete this, you need a kind of inductive argument. And I want to just explain briefly how that goes. Because now you can ask, right, if you want to prove Andre-Oort, then eventually you have to prove that there are only finitely many maximal specials here. So for the moment, we've proved, if you like, that there are only finitely many points that don't lie on something positive dimensional special, because they're weakly specials and they contain a special point. But how do we know there can't be sort of some infinite number of these things that have increasing degree? And now there's a nice inductive argument, and it uses O-minimality in a very nice way. Because the weakly special subvarieties come from a partition of the coordinates in which, and some coordinates are constant. These are constant, these are non-constant, and related by GL2Q. And so now we can view, if you like, this constant, or of each of these varieties of this form, of being translates, in some sense, of this one. It's a bit like, I mean, they're not really translates of this one because, well, but you can call them that. In any case, and now you can consider a larger family of things which look exactly the same. Some constants, some coordinates are constant. Then you've got a partition on which everybody is related not by GL2Q, but by GL2R. Simply by 2 by 2 real matrices with positive determinant. So we call these Möbius varieties because they're varieties defined by Möbius transformations. But this is a fully definable family. In fact, over all the there are only finitely many partitions, and these constants are just elements of the upper half plane. That's semi-algebraic, right? This entire family of Möbius varieties is fully definable. And now I've got this definable set Z, which is in, right? Oh, it's the same Z as over there. So now I can look at the definable family of intersections. So this is a definable family in some big Rm across h to the n. And there's a Möbius variety y for every y here. And I can look at the family of intersections. And I can look for when, so whenever a weakly special subvariety is actually contained in the preimage of V, then after some transformation, you'll find that this thing intersects in the fundamental domain. It will be of dimension equal to the dimension of the variety. So I can look at the family of Möbius varieties which intersect Z in the full dimension, and that means that so secretly that means that that Möbius variety is contained in J inverse V. It's not a reversible implication because some Möbius varieties may miss that set. It's not the whole inverse image. But every Möbius variety, that does, would have a translate under SL, a transform under SL2Z which did. But in any case, the point is I can now look for the Möbius varieties which are maximal with that property, that they're contained in this, that they intersect Z in their full dimension. That set is a definable set, but by Ax-Lindemann, everything in that set is actually defined by GL2Q. And this is over all translations. So I get a definable set in which every element is a rational number, and that can only be a finite set. And that tells me that of all the weakly specials that are contained in V are all translates of finitely many. And then I have an inductive argument which says on each one of these, for each one of those families, which translates are contained in V, and that gives you a lower dimensional problem of the same, a lower dimensional Andre-Oort problem in Yn. So I think that's a very nice illustration of how O minimality can work in this kind of thing. Right. So this template that I've described here can be applied generally to Andre-Oort and indeed to the generalized Andre-Oort, a special point problem in mixed Shimura varieties. They all look like this. You have, maybe I should write, instead of this picture, you have a similar picture where the variety in question, the mixed Shimura variety, is uniformized by some domain, right? And there's a discrete group acting, and you've got a fundamental domain which may have cusp. And the special points here always correspond to points here of some bounded degree, because they're fixed points of some matrices of fixed size. And Emmanuel set out how, in general, all these four ingredients give you the Andre-Oort conjecture. And over a period, all of these things were established in general. Each one, in fact, turns out, well, I mean, the definability here was quite trivial. Peter Zil-Starchenko did it for the Siegel modular varieties, and then Klingler, Ulmo, and Yafeyev did it in general. It required revisiting somehow the toroidal compactification of these Shimura varieties. This, which is a totally elementary computation, turned out to be quite an exercise in reduction theory in general. It was done by Dorr and Orr. Ax-Lindemann was gradually established well, in great generality, again, Klingler, Ulmo, Yafeyev, and me and Jacob Zimmermann, and then in even greater in Ax-Shanwell and in variations of Hodge structures and mixed Hodge structures and so on. And in a way, the hardest ingredient, or at least the last one, was the Galois orbits. And in the Siegel modular case, Jacob Zimmermann got this size of the Galois orbit, which is in general not a class number, but the size of an image of a class number, one class group into another class group, that using isogeny estimates and something called the average Kolmez conjecture, which is a precise conjecture on the height of the special points in general. But the general moral, I guess, is that that with definability and this functional transcendence principle, that the O-minimal setup, if you like, gets rid of the geometry and reduces you to some purely arithmetic things which you may or may not be able to establish. Right. Okay, so I'll take a break. Okay, so I guess I'll make a start. So I wanted to mention, I didn't wipe out those ingredients. So I wanted to mention what I think is a very nice idea of how to use point counting to make some progress on this size of the Galois orbit. So this is a crucial element in this scheme, and in some sense it's sort of the hardest, that you want to prove that these special points have quite large Galois orbit. So let's talk about this a little bit. Point counting for Galois lower bounds. So this is an idea, the idea for doing this due to Harry Schmidt and implemented by Binyamini, Schmidt, and Yafeyev based on a counting theorem of Binyamini. So the idea is, let me go over here a little bit, that if in the general picture you've got some domain D, which uniformizes your Shimura variety, say, let's call this U, and it's definable on a fundamental domain. So now I'm going to take G to be the graph of U restricted to the fundamental domain, and this is a definable set. So it maps from this F onto X. That's definable. And the idea is that if you have a special point in X special, the special point is algebraic. Its pre-image in the fundamental domain is also algebraic and in fact of bounded degree, but the special point, so let's call this X and this Z, the special point Z X is an algebraic point on G. Now, what one tends to know in this situation is that X, we want to prove that X has a large Galois orbit. And that's the goal. But what we do know is that for a given description, for a given discriminant, there are actually quite a lot of these x's. Some class number, many of them. They may not be all conjugate. But they all give you algebraic points on this graph, and they have these x's have a fixed bounded degree. I mean, it's not, once you fix the type, the x's, the special points don't have bounded degree, they have high degree, but once you fix a type, a discriminant, somehow, you get a lot of these points that do have the same degree, and they come from points that really do have a bounded degree. And so the idea is that if your counting theorem is strong enough in its dependence on k, well, and the height, as we'll see, if you have a strong enough counting theorem, then you can force the degree to be large if the height is small. So I'm going to go through how that works in the modular case. But we have to, I'm going to go through that in the modular case. So Well, let me write down the counting theorem first in this situation. So suppose we have x, which is defined over a number field, L, and I've got this definable set, capital G. So let's take z equals g, just because I like to count points on z. And now I'm going to take a new counting. I'm going to count the points on z up to degree f and logarithmic height h. And I'm using a square bracket to distinguish it from this. So this is the set of zx's in z, such that the degree of the points over the defining field of x is at most f, and the height of the points involved, let's say the maximum of the two logarithmic heights, is at most h. And keep in mind that h is the logarithm of the naive height, the multiplicative height. And then the theorem is, in this situation, so this is Bignamini's counting theorem. And I should say this counting theorem doesn't apply to a general definable set, as we know it couldn't, and even not definable in R-FAF and so on. But this is quite a different picture where this graph is the leaf of a foliation of a suitable differential equation. So this is quite a special counting result, but he can prove in this case that the number of points on Z whose degree is at most f and whose logarithmic height is up to h is at most a constant times some power of f and h. And keep in mind that this h is log h, right? So this is not only replacing this t to the epsilon by a logarithm, but by saying that this constant can be replaced by fixed polynomial power. Now, so what happens in the modular setting? Now, in the modular setting, it's a basic theorem that all the special points corresponding to a given discriminant of a quadratic order are conjugate.
So there is no algebraic part.
Yes, I should have said that. Yes. Yeah, no, thank you for that. I should have mentioned it. So this graph G has no algebraic part. The algebraic part is empty, because if it had anything in it, you'd have something algebraic here on which this uniformizing function were algebraic, and it's a transcendental function. So there is no algebraic part of this. Yeah, thank you.
Something which is algebraic upstairs and algebraic downstairs could be just something weakly special. No?
Yes, of course, the things that are, whose image, the algebraic things here, whose image is algebraic, are exactly the weakly specials, but there is no algebraic part in the graph, because that would amount, as I said, that you'd have some variables upstairs, and then the variables downstairs would be algebraic in them. Whereas when you have a weakly special here and its image here, there's still a transcendental, going from here to there is still a transcendental map. Right, so this algebraic part is truly empty. So in the modular setting, all the special points are actually conjugate, and there are a class number of them. But we're going to just pretend for a minute that we don't know that, or we just forget it. And then what it means is that you have, and we also know that the height of a special point, the logarithmic height, is less than or equal to a constant discriminant to the epsilon. This was the key thing in the general case of Andre-Oort, or the Zimmermann case in the Siegel subvarieties. You wanted to know this kind of estimate, which came from the average Kolmez conjecture. And this is tied up with the L functions of the quadratic field and the Siegel zeros. Okay, so this is, well, this is the L function. This is from the same world as the Siegel zero and the Kolmez and this. But so if we, on the other hand, there are a class number of them. So if we forget that they're all conjugate, and so this class number is actually the degree, f, in there, and if we apply this theorem, it would say that the number of points, t to the half minus epsilon 1, so this is the number of, number of points, which is at least, let's say, t to the quarter, if we choose that epsilon 1 correctly, that number, by the counting, is less than some constant times some epsilon 2 for the height, times f to some other constant, which, say, is less than or equal to some constant times discriminant. This epsilon I can take to be what I want, so I'll take it to be 1 over 10c, f to the c. Right, this is because I know that the height of these points is rather small. And then I'll conclude this d to the 1 over 10c to the c comes off that quarter, and it will tell me that this f must be at least some constant times something positive. So here, all we really used was that there was a lot of these points. And of course, in the application, you want those points you want points with large Galois orbits so that they don't fall off the variety they're sitting on. But you can't fall off the graph. So if there are a lot of points, they're all on that graph. Right. So you can do this argument in the general case, and you see that if the height is discriminant negligible, then the degree must be large. And this is how Andre-Oort gets reduced to proving that the height of special points, well, this is one way of doing it. Jacob did it with isogeny estimates because it was before this was there. But you see it here that if your counting is strong enough, you can reduce the degree lower bound to a height upper bound. And then that involves, as I say, this average Kolmez conjecture. I also wanted to briefly mention point counting for Ax-Lindemann, which used to be the way it was done, but there is now a better approach. And by better, it means more algebraic. So this Ax-Lindemann and the more general Ax-Shanwell are really, in a certain sense, they're pure algebraic statements. You can formulate them in differential algebraic fields that if you have solutions of certain differential equations, you must get certain transcendence degree. It's a kind of a algebraic statement. But for a while, all the proofs went via point counting and O-minimality, which I'll just sketch briefly. But now so that's, in some sense, that was a bit odd to use counting to prove something like that. And there's this better, more algebraic approach due to Blasquez, Sands, Casal, Freytag, and Naglu. So that uses more Cartan theory of principal bundles and differential algebra and also some model theory. But I like to explain this idea, which this idea could still be useful. So the idea is this, and maybe I'll just try and draw this picture. Let's imagine that we're in the upper half plane to the n, and this is f to the n. Like that. And we do our point counting. We have some v. Here is y1 to the n. And there's some subvariety v. And we've got some set z here. And we do our counting and we find something algebraic. So here it is. Here's an algebraic w which is giving us something there, and which we know, well, for the moment we don't know it's weakly special. It's just something algebraic. But the idea is, of course, that there are many translates of this fundamental domain under SL2Z. And so if I translate this fundamental domain here, then this thing will also be in there. Because the uniformization is invariant under SL2Z. And by analytic continuation, this whole algebraic set W is in the pre-image. And so if I translate it there, I'll get another picture. And if I do it here, I'll get something else that's there. And so now I can look at a definable set, which I'll call Y, which is the set of gammas in SL2R to the n, such that gamma W intersect Z, the dimension of that set is equal to the dimension of W. This is, well, it doesn't you can use whichever dimension you want, but the point is if it intersects this set Z in the full dimension, that's a code for W being the full W being inside. Now here I've taken these gammas are in SL2R, and gamma W, the action is fully definable and semi-algebraic. This is a definable set. So this set is a definable set, but every time I take a gamma that this W goes through, if it goes through this gamma of the fundamental domain, or it might just be gamma inverse, then that translate will be in the set. So this set Y contains a lot of elements of SL2Z. And you can prove that this W has to go through an awful lot of fundamental domains. And then you'll get a definable set that has many integer points up to a certain height. And you'll conclude that this set Y contains something positive dimensional, semi-algebraic, and you complexify that parameter, and that'll tell you that you can try and make W bigger. That you can somehow, you can take a family of these W's, and the conclusion of this argument is that if you took your W to be maximal, then it has to be stabilized by those translations. And so now there's sort of group theory kicks in, and you show that the sets W that have enough stabilizers, because you can do this in very many directions, have to be weakly special. So this is an argument, it's a point counting argument for Ax-Lindemann. Right, and as I say, that's sort of been superseded by this more algebraic approach, but it may be that this argument, it's quite a different kind of argument. You're not looking at points inside V, you're sort of looking at what's happening outside in this full uniformizing space, and the rational points are now coming from the arithmetic group. So it's somehow, it's different. All right, so now I want to get back to unlikely problems. And I want to show how you use this strategy to deal with a simple problem in unlikely intersections. And maybe the first thing to say there is what my goals are in doing that. And it's firstly somehow to show, how that application goes. What is what is it that you're counting? How does this become a problem of rational points? How are you counting? And then also to talk a bit about the arithmetic involved. So the simplest kind of problems, so the simplest ones are where X will be a Shimura variety or a group variety, and you have of dimension 3, so dim X equals 3. The dim V is equal to 1. And you consider intersections V with special subvarieties of X of dimension 1. 1 plus 1 is 2. The ambient is 3. So this is intersection is unlikely. And the Zilber-Pink statement, just to recall, says that the union of these V intersect T's over all T's with T, dim T equals 1 and so on is a finite set and there's a conclusion unless V is itself already atypical. So this is unless V is contained in some T prime, which is special and whose dimension is 2. If V is in a special subvariety of dimension 2, and that special subvariety will contain lots of these T's of dimension 1, and then 1 plus 1 is 2, and it's not unlikely anymore. And in fact, it's a likely intersection. And there's a bunch of theorems which I won't talk about, but essentially likely intersections are essentially always infinite and Zariski dense. So it's a necessary condition. And we can also recall the theorem of Morin, which is ZP for a curve V in GM3. For GM3, it's actually due to, it might be Bombieri-Massezenia. Anyhow, for a curve in GMN. Right. Now, I also mentioned the Legendre family of elliptic curves. And we can consider also the fiber-wise square of the Legendre family, which is the family of elliptic curves squared over lambda in y2, which is p1 minus 0, 1, infinity. And so the dimension of L2 is 3. That's a three-dimensional variety. And I explained how Zilber-Pink implies the Manin-Mumford conjecture, let's say for something like E lambda squared. And the picture there is that you have your y2. And over each point in y2, you have this E lambda squared, which is not special if lambda is not a special point of the base. But if you have a subvariety here, let's say a curve of dimension 1 in E lambda squared, then the torsion points there are intersections with torsion sections, and they're unlikely, and so on. So Zilber-Pink implies Manin-Mumford. But in this picture, there's no reason to restrict this variety V to be in a vertical fiber. And you could also consider V's to be just in the three-dimensional space. If they're not confined to a fiber, then they'll be dominant to the base, which is only one dimension. And now what you have is relative Manin-Mumford, because the intersections of this curve V with the torsion sections are still 1 plus 1 in a three-dimensional space. So this is what's called relative Manin-Mumford problem. When you're on a curve in a fibered space of abelian varieties, so that every point in your variety is in some different abelian variety. But at each point, you can ask, am I torsion? If this V, is it a torsion point? At each point lambda, is V of lambda torsion in E of lambda squared? That's a relative Manin-Mumford problem. And you had a series of results on this by Massa and Zanya. So maybe I'll just write down the very simplest one, where they considered V to be the set of points at each lambda. You take the point in E, in one of these coordinates, the point whose x coordinate, so this E lambda, of course, is defined by y squared is x minus 1, x minus lambda. Maybe I won't even write it down. They took the point with coordinate 2, which in general is generically non-torsion, and the point with coordinate 3, which is generically non-torsion. Those 2 points give you a point in E lambda squared, and they proved initially that there were only finitely many lambdas for which that point was torsion in the abelian variety it was in. So then after there was a series of results of Massa-Zanya for two-dimensional abelian schemes, and then our relative Manin-Mumford fully proved in general by Gao and Haberger. So this is for subvarieties of abelian schemes. So that is I'll take that out, but I'm actually assuming we're going to have a similar bunch of ingredients. So the problem I want to talk about is the simplest unlikely problem in a pure Shimura variety, the case of a curve V in y1 cubed. So let's let V be a curve in y1 cubed. And again, as in all of these theorems, we'll assume that V, all right. So ZP predicts what it always predicts. It predicts that if you intersect V with one-dimensional special subvarieties, over all the one-dimensional subvarieties, you get only finitely many points, unless V is itself contained in a proper special subvariety. So I'm going to assume that we're not in that case. Not contained in a proper special subvariety. And by proper here, I just mean a strict one that's not the whole space, because the whole space is special. So I don't mean properness in the sense of maps, I just mean proper in the sense of subsets. Okay? So the prediction is that only finitely many, so the number of points, so the union of V intersect T over all special T, one dimension, special and dim T equals 1 is a finite set. That's what ZP predicts. Maybe this, I should say right away that this problem is open in general. I'm going to describe a strategy and which can prove it in some cases and under additional assumptions and so on. Right. But let's recall that such T take a few forms. What are the special subvarieties of dimension 1? Well, you could take T to have two special coordinates. Two of the coordinates are special and the other one is free. That's like the analog of a vertical or horizontal line in Andre's theorem. Or, so remember again, I think I've probably wiped out, but when you have a special in y1 to the n, right, it comes from a partition of the coordinates, some of which are constant and some of which are related by modular relations. Here there are only three coordinates. You can either have 0, 1, or you could have all three constant. That would be a special point. So you could have two constants, or you could have one constant and one modular relation. Let's say on y and z. Let's say x is constant and modular relation on y, z. Or you could have two modular relations, and that will mean that all three coordinates are pairwise related by modular relations. So you might have, I'm going to recall that NM. It doesn't, okay? So this is somehow the shape of one-dimensional special subvarieties. Now, these are covered by Andre's theorem, that's Andre-Oort. If you project your curve onto the two coordinates that are special, then you will get Andre's theorem that there are only finitely many points like that, and there are only finitely many choices for those two coordinates, unless y in that projection is a special subvariety, and then the unprojected one will be contained in the cylinder over it. So this kind follows by Andre's theorem. I'm going to talk about case 2 at the end. So I want to really talk about case 3, which in some sense is the generic case, but all of these cases are countable, so you can't really. But I'm going to talk about this case, and then at a certain point I'll say how it is that you can deal with this case. This is from actually from my paper with Habeger, where we proved some results. Well, we proved a number of results, special cases or under additional assumptions. I'm going to actually explain mainly what that result is. But we can deal with this case. And I just want to also make the point, because before we all get sort of buried in arithmetic, the key point here is that when one coordinate is constant and special, I should have said, the special point has low height, and that controls the height of the other points on the curve. That'll turn out, I mean, that'll be a key issue that comes up probably next week, talking about the arithmetic that comes in here. But the key is that once you've got a special point that's constant on the curve, it somehow controls the height of everybody. And so in here there are various partial results. So there's a sum due to me and Habeger, to Dor and Or, and to Papas, which depend on extra hypotheses. Let's say we can prove finiteness under extra hypotheses. So somehow in general this problem is open. Right. Now I want to introduce the complexity of a special subvariety T So in general, okay, in this problem we're only really concerned with specials of dimension 1, but this notion is fully general to any special in any y1 to the n. The complexity of a special variety is the maximum of all n that come up with in defining this special subvariety, you have a number of modular conditions, and of all absolute values of discriminants of any constant coordinate. So when you define a special subvariety, you'll have the partition that I've got on the far side of the board. A number of coordinates will be special. They'll have discriminants, which are negative. So you take the absolute value. The other coordinates are related by modular relations, and you just take the maximum of all the n's. Now, there's a slight point that when you do that, if there are a number of points here, then they will be pairwise modular related. So for example, here I wrote down two modular relations, but they will entail a third one between x and z, because the elliptic curves with these two J invariants are isogynous, and these two will also be isogynous. But this L, it could be as much as n times m, or it could be as small as 1. On the other, so in fact, but somehow all our dealing with this complexity will only be up to some positive power. So it actually doesn't matter. If you like, you can assume I take a maximum really over all n's, so even over this implicit L, or only over the n and the m that relate. So long as you have everybody related, you'll have the same complexity up to some fixed powers.
Can you take the degrees of the curves?
You could take the degrees of the curves. Yes, it would be a bit nicer. This is somehow just more, yeah, more concrete. All right, so these also are what's known as the strongly special subvarieties of y1 to the n, the one with no constant coordinates. And so what I'm going to do is essentially sketch out the theorem that Habegger and I proved, but somehow instead of proving it under the assumption that we did it, I'm just going to put down the conjecture that we ultimately use. So, as in Andre-Oort, the lower bound for the Galois orbit of the points you're looking for is the hardest thing. In fact, in this case, one only has rather special results. This is what I'm going to write down here is open. But I'm just going to put it there up front and then proceed with the strategy. That if the points you're looking for have a reasonably large Galois orbit, then you will prove the theorem. So again, I'm going to assume that V is defined over a field L, and this is a finite type field. That you have a constant, let's say, well, you can view of them as being, depending on the variety or the field, if you happen to take a bigger field, that you have constants such that for a point x bar in V intersect T, where T is a special T special, and the dimension of T is 1, that the degree of Lx over the base field L is at least a constant times the complexity of your special subvariety to power delta, positive power of this complexity. All right? So I'm going to come back to that to discuss this conjecture. So the theorem, maybe I'll just put the theorem over here. This is my theorem with Philip Habegger. That if you assume that this LGO for the variety V, then Zilber-Pink holds. This is for a particular variety V. All right? So it's a counting argument, and somehow what it tells you is that everything comes down to knowing that the points you're looking for have a reasonably large Galois orbit. And I'm going to assume also for the moment a stronger condition on this variety V, that it's not contained, V not contained in any proper weakly special subset. But then at a certain point I'll explain how this case is the case that it is contained in a weakly special is actually much easier. But it's convenient to not to deal with that. All right. So I've explained, so we're going to consider that there are these two relations, and there's also implicitly this other relation. Right. And so now let me come back here. I can Right, so now we've got 3 copies of the upper half plane, which map down to y13. And in here we have some curve V, and these are my 3 copies of the fundamental domain for the SL2Z action. And so we can take Z to be the pre-image of V intersected with this product of upper half planes, and that's a definable set. Right. But of course the intersections of V with T are not special points anymore, so their pre-images won't be algebraic, and we have to count something else. And what we're going to count is the description of T. So now I'm going to say that for alpha and beta, which are in GL2R with positive determinant, Y alpha beta is the set of Z's Z1, Z2, Z3. In H3, Z2 is alpha of Z1 and Z3 is beta of Z2. So this is a Möbius subvariety in H3. And of course, if alpha and beta happen to be rational, then this will be the pre-image of a special subvariety. All right, so this is a definable family. And it's even, it's just a semi-algebraic family. And now the source of the rational points is going to be this if Z is the pre-image of some tuple X with X in T. And so in particular, if it's in V intersect T, the pre-images of special subvarieties are going to look like this, but with alpha and beta rational. Then there exists alpha and beta in GL2Q with Z in Y alpha beta. And so, if you like now, there'll be something corresponding to the height ingredient. Maybe I'll leave that till next time so that I can still say this. So we get a rational point. So we get a rational point So keep in mind that this y alpha beta is still one complex dimensional, and the pre-image of z is also one complex dimensional. Of course, it's cut off, it's not nice. But we're still unlikely, so to speak, on dimensional grounds. So I'm going to take x to be the set of alpha beta in GL2R squared, such that y alpha beta intersect z is not empty. That's a definable. So this is a definable family because I'm still in the reals. Z is a definable set. The set of parameters for which that intersection is not empty is a definable set. And on the other hand, if you have a point which is in the intersection of V with a special subvariety, then you'll get an alpha beta which is in fact rational. You'll get a rational point on this set. And that's where we're going to count. And the first thing we have to do is be a bit more specific here, because it's not enough to get a rational point. You have to control the height of that point. So this will be the height ingredient, which I'll get to. But maybe as a final remark at this point, that just to observe that we have a problem, which is that this variety X is fibered by stabilizers. If you have an alpha beta for which this intersection is non-empty, then you can modify alpha and beta by any stabilizer of those points in GL2R. And so this set is completely, its algebraic part is the entire thing. And that's why I kind of went through all that statement of the counting theorem with the blocks, with the pieces you get, because that's what you have to use here. Even though the algebraic part is everything, the counting theorem is still going to tell you that your rational points, which you're going to get a good height ingredient, and on LGO we get a Galois lower bound, they do lie on a small number of semi-algebraic pieces in this set. And let me just say, now we'll come back to it, but as a final statement, the key point is that these blocks, of course, they could somewhat hide inside stabilizers. You could imagine, why don't all these blocks simply hide in the stabilizer of one point? And the reason is that we're going to have a lot of points here to account for. T to the delta from our Galois orbits, and T to the epsilon blocks. So if each of these blocks was hiding in the stabilizer of one point, they would not account for all the rational points you got. And so some of those blocks have to be, so to speak, not confined to stabilizers, and the intersection points have to move on, and that will be the key point that makes this argument work. So we take that up again next time. And then I want to talk more about the Galois orbits and the heights and the arithmetic. Okay, so I stop there for today. Thank you.